How's it going, everyone? This video is going to go through lesson B3, which is all about characteristics of something called a logarithmic function. And we're going to take a look at two different kinds, base 10 and base e, and we're going to talk about what those mean. Now, in the version of the notes that I'm using, there are a lot of typos in it right now. But hopefully in the version that you are using whenever you're watching this video, they are fixed. But make sure that you follow along and just pay attention to where the mistakes are. So the first mistake is right here in the first sentence, which says the expression log 10 of x. That's what it should say. This is called the common logarithm. So like if you ever look at a calculator and slowly throughout high school, you kind of unlock more buttons and the meaning behind more buttons. On a calculator, there is this log button right here. And if you look above the log button, there is a 10 to the power of x, which is an exponential function. Okay, so log base 10 of x is called the common logarithm, or it's called a logarithm of base 10. That's why there's a 10 written there. But you can see here on the calculator, we don't have log with a 10, we just have log. So usually the expression, we write it without the 10, it's just implied that, that the 10 is there. Okay, so if you see something that says y equals log 10 of x, or if you just see something that says y equals log of x, they both mean the exact same thing. What a logarithm is, so if we're talking about log base 10 of x, what that means is we are trying to solve for this, it's this equivalent expression where we're saying that x is equal to 10 to the power of y. So it's kind of like the inverse of, we're going to talk about inverses in a little bit. What this means, log base 10 of x, is we're looking for the exponent that must be applied to the base of 10 to get the value of x. So for example, if we are looking for log base 10 of 100, that is equal to 2, because 10 to the power of 2 equals 100. Okay, just to kind of show you here, if I do log of 100, it equals 2 on the calculator. There's no 10 there, the 10 is implied when we use the log button. Okay, similarly, if we said log base 10 of 10, is equal to 1, because 10 to the power of 1 is equal to 10. And there's another kind of log as well. So again, if we look at the calculator, we have this log button here. Below that is something called ln, which is the natural log. That's what that means. And that's equivalent to a number called e. And I don't know if the number e has ever come up at all in any prior math learning, but the number e is equal to 2.718281828, and it continues on from there with a whole string of numbers. Okay, so this is the, it's called the natural logarithm. That's what we use ln for. And we write it as y equals ln of x, which is the equivalent of y equals log base e of x. Now, all of this isn't necessarily important to what we are going to be talking about in this lesson, but just some kind of background information of what these two buttons mean, because we are going to be seeing them in our calculations. Okay, we have two functions here. We have our log function and we have our natural log function. So our log function is f of x is equal to log of x, and the natural log is equal to f of x is equal to ln of x. And you can see that they both have the same shape to them. But the interesting thing about these two functions is that they are the inverses of the exponential functions that we looked at in the previous two lessons. So what an inverse means is if we draw the line y is equal to x, inverses are reflections on that line. So they are reflections, or if you want, they're like mirrors of each other. And in this case, my mirror is the line y is equal to x. So this is my graph of y equals e to the power of x, and this is my graph of y equals ln x. Same thing here, this is my graph of y equals 10 to the power of x, so an exponential function, and this is my graph of y equals log of x. So they're reflections of one another. Now, we're still going to be talking about the characteristics. We're still going to be graphing them using Desmos. But just some characteristics that you should know. Again, sorry, there are a bunch of typos here, so I'm going to cross those out. So whether we are talking about the graph of log of x or the graph of ln of x, there's only going to be one x-intercept, and there is not going to be a y-intercept. So this is going to be the one case of a function where there is no y-intercept. Okay, these two characteristics are flipped from our exponential functions. So exponential functions had no x-intercepts and it had one y-intercept. So these are opposite of exponential functions. And again, that comes back to the whole idea of the fact that they are inverses of one another. We can also still talk about the end behavior. So if my a value of my function is positive, that means it's increasing, so it's going to be going up like that. And my end behavior starts in quadrant 4, goes to quadrant 1. If my a value is negative, that means that it's going to be decreasing, and it starts up here at quadrant 1, and it goes down to quadrant 4. So maybe some good information to write on a cheat sheet. The domain is always going to be either x equals 0 or from 0 to infinity with curved brackets. The range will always be YER or minus infinity to infinity with curved brackets. So what we're going to do is we are going to graph these two functions here using Desmos and taking a look at the characteristics of each. Again, there's a double log here, so I'm going to cross those out. Those are just there by mistake. So the first one we're going to take a look at is f of x equals 2.5 log of x. So I'm going to switch over to Desmos, which I have open here. And I'm going to type f of x equals 2.5 log of x. And so this is my graph here. Just a couple of things to point out is, again, my graph gets very, very close to the y-axis, but it will never cross it. That's why we have no y-intercept. It does have an x-intercept at 1, 0. And you can see that my graph kind of levels off and curves towards infinity. Okay, so if we go to graph this, so we know that there's an x-intercept at 1. We know that it's going to approach the y-axis but never cross it. It's going to hit that point of 1 and then it's going to take off in that direction there. So it looks something like that. And like we said, it's the inverse of our exponential function, so it has the same sort of shape to it, just pointing in a different direction. So we're going to determine each of the following characteristics. So if my x-intercept we saw was at 1, 0, there is no y-intercept, and there never will be, at least in this course. But once you start, if you were in pre-cal, there would be some transformations that could happen, which could lead it to get to a y-intercept. But for our purposes in this course, there will not be a y-intercept. The end behavior starts in quadrant 4, and it goes to quadrant 1. So quadrant 4 to quadrant 1. Domain is 0 to infinity. Range is negative infinity to infinity. So even though it looks like in the graph that it kind of levels off, keep in mind that's only the beginning part that we can see. But as it increases infinitely to the right, like once we get into the millions and the billions and so on and so on and so on, it's still going to keep slowly increasing to a certain extent. Okay, but the point is it is always going to go to infinity. The last thing that it is asking is if it is increasing or decreasing. So our a value is positive, which means my function is increasing. All right, we're going to take a look at one more, negative 4 ln of x. So again, let's go ahead and flip back to Desmos and see what we get. So negative 4 ln of x looks kind of like this, looks a little bit like a slide. Interestingly enough, the x-intercept again is at 1, 0. You might notice a pattern as you graph these and find the value of the x-intercept. But this time it is going down like it's a slide. So again, if we kind of scroll up a little bit here, it gets very, very close to the y-axis, but it never crosses it. It hits the point of 1, and then it kind of curves out to the right. So if we go ahead and draw this one, again, we have a y-intercept, an x-intercept at 1. It's coming down from the y-axis. It hits that point, and then it starts curving outwards. So again, this has the same shape as the previous one that we just drew, except now it is, instead of increasing, it is a decreasing function. So my x-intercept again was still at 1, 0. There is no y-intercept. The end behavior for a negative logarithm function goes from quadrant 1 to quadrant 4. The domain is still 0 to infinity. And again, with curved brackets, my range is still negative infinity to infinity because it does continue downwards to negative infinity, just kind of evens off a little bit. And then this is a decreasing function. So depending on which version of the book you were using, just kind of watch out for those typos. Sometimes there's a double log written. Those are all there by mistake. So just kind of watch out for that, and just make sure that you're familiar with the characteristics, and there will probably be some questions that will ask you to find some information based on these graphs. So make sure that you are prepared for those as well.